This video is about an in-class quiz for Chapter 8. You didn't get one in class, but just for your own purposes, I figured I'd go over one anyway. So you could have gotten this one, for instance, had I given a quiz on Lecture 8, on the reading assignment for Lecture 8, the reading assignment, Chapter 8. Here we've got a conductor, and it's been charged and is far from everything else in the universe. In class, the day that I am making this video, we talked about the capacitance of a pair of conductors. One can also define a capacitance for a single conductor, and that's what we have here, where for the case of a single conductor, the charge is simply the amount of charge on that single conductor. When we're talking about the capacitance of a pair of conductors, it's understood that in charging that capacitor, one has moved a certain amount of charge from one plate to the other, leaving one with a certain amount of negative charge and the other one having the corresponding amount of positive charge. So the two absolute values are the same. One conductor has a negative amount of charge and the other has a positive amount of charge. The two amounts are the same in both cases. It's the algebraic signs that are different. But here we're talking about a single conductor, and the capacitance is Q over phi, the charge on that conductor divided by the potential, the electric potential of that conductor, with the understanding that the zero of electric potential is at infinity. So how does the ratio Q over phi vary? Well, the ratio Q over phi is the capacitance of the single object, and that's a constant. So as you increase Q, phi increases in such a manner that the ratio is constant. We can say that Q is directly proportional to phi. That means Q is equal to a constant times phi, and the constant of proportionality is capital C, the capacitance of the object. So how does it vary? It doesn't. It doesn't vary, it remains constant. That would be this one. Alright, it doesn't vary, it remains constant. So now for a parallel plate capacitor, so we got the two conductors, the kind that we talked extensively about in class. What do we mean by the charge on the capacitor? And the amount of charge on the positive plate, that's certainly true. The amount of charge on both plates together, that's always going to be zero when we're talking about the charge on a capacitor. In this context, the total charge on both plates together would be zero. So what we mean by the so-called charge on a capacitor is the amount of charge on the positive plate. Alright. What happens to the charge of a parallel plate capacitor if you increase the voltage across the capacitor without changing the arrangement of the plates and without changing what kind of material is in between the plates? So C is a constant if you don't change the physical characteristics of the capacitor, and we're assuming that you don't change the size of the plates either there. It's hard to do that. But Q is equal to CV. What happens to the charge if you increase the voltage? So if that goes up, given that this is constant, because we're not changing the physical structure of the device or the arrangement of the plates making up the capacitor. So if this goes up, then Q has to go up, so Q increases. So read that one more time. What happens to the charge, Q, if you increase the voltage? V goes up, and therefore Q goes up. That's C. Alright, that does it for this video about an in-class quiz on Chapter 8.